Hello, this week I want to talk about geostatistics for groundwater modeling. So you can have a full lecture or a whole studies about geostatistics and statistical methods in general, especially then also in context with GIS software. That is not my aim here and today. I just simply want you to show how you can use geostatistical methods within your groundwater modeling system. So there have been a couple times we talked about statistical distributions of parameters, for example, to represent heterogeneity, for example, to generate fraction networks based on statistical parameters obtained from the field. This is what I want to talk about today. So we usually, when we do groundwater modeling, have the task to conduct simulations over a whole domain. And if you are lucky in practical applications, you will have a couple of borehole measurements, lab tests from borehole cores, which are somehow distributed across your modeling area. So based on this very sparse information, an exact description of the system is an illusion, right? It's not economically possible. It would require an unfeasible amount of work. So whatever we use as parameters is by definition associated with some kind of uncertainty. But we have to make sure this is not an uncertainty in terms of as an intrinsic property of the system. This is a result of an incomplete knowledge that we have about our system, about our aquifers, about our modeling domain and our parameters. So we can just try our best to cope this uncertainty by, for example, parameter variations, different kind of assumptions, doing scenario testing, and of course trying to characterize our system, which also in groundwater modeling of course is always related to some kind of spatial dimensions, in the best way possible based on this incomplete knowledge that we have. So you might know that, but quickly giving you an idea about what I'm talking about is how can you assess spatial heterogeneity. This very much depends on your scale. So if we're talking about laboratory experiments or borehole cores, this will give us information very, very locally. A couple decimeters, maybe meters of validity. When we do push and pull experiments, pumping experiments, this will give us in the meter scale up to decimeters, maybe a couple hundred meter scale, right? If we also throw in tracer experiments, we can go in meters to kilometer scale. Of course, there are also other methods, tomographic models, geophysical methods, which cover a wide range. You can apply decimeter scales, meter scale if you're talking about electric resistivity. You can go to kilometer scale if you go like airborne magnetics. But of course, larger the scale, the coarser the information. So it also depends on your modeling scale. So you need to get those one overlapping. So the spatial heterogeneity and the methods you have to assess your spatial heterogeneity based on your model resolution and your model scale. But there are a couple of things we can get hydrogeological information for our groundwater model. But what we have is we need to interpolate, right? I just want to make that clear here is we have some spatial information and we have maybe gaps in between those. And what we do is we interpolate between those gaps. We can do this linearly, as it's done here, or we could do it in some kind of curve. This is what we do for one state in time. do not get confused with an extrapolation. So what we do in also numerical modeling is looking forward in time. So what might happen if different incidents take place, for example, pumping or stuff like this. So what we do is we have our past record of maybe simulations of the past, and then trying to go forward to see what might happen in the future. Okay, so this is different kind of parts we're doing in modeling. Doing extrapolation, so looking towards the future, and interpolation in the spatial scale. And well, what you do is you do statistics. All right, you have a couple of samples. You build some kind of categories, and you see how many samples you have per category, right? And then you can do some kind of statistics, and you see, well, okay, if porosity, most of the samples somewhere 5% porosity, so you get a distribution, right? That is simple statistics. You can do this. Make sure, of course, you need to have 100% of the samples in the end. But this is just simple statistics. You have just one variable, you do your statistics. And there are a couple of vocabularies, terms you should know. Well, you all probably know the arithmetic mean. That is just, well, summing up, making the average, dividing by the numbers of samples. We have the median value, which is just simply splitting my numbers of observations in between, right? So if you have 75 samples, we would have not at the 50, but at the 75 divided by 2, 37 samples. So this would be somewhere here, my median value, because I mean half of the samples are lower than this value, which would be here probably around 5.0. Half of the samples will be lower, half of the samples will have a higher value than this one. The mode is the most probable or most frequent value. Means you have your distribution, it gives you, well, okay, most of the samples have or fall in the category between 5 and 6%, right? So this would be here. You see that's my strongest slope. Most of the samples have that value. That I would call the mode. You can also compute different kind of means based on your samples. The arithmetic mean, I already said, sum everything up, divide by the number of parameters you have. The geometric mean means you take the square, not the square root, but the root of the order equal to the numbers of samples you have, and you multiply all your values. And the harmonic mean would be the reciprocal sum of all parameters, and you have the numbers of samples divided by this sum. What is all those kind of geometric means good for? I mean, that's just formulas. You can calculate those ones. The arithmetic mean you all know. The geometric mean is especially interesting if you have distributions with a large variation in magnitude, right? If you go for hydraulic conductivity, it's not unusual for us to have several decades of magnitude covered within different samples, because it just varies so strongly between the different kind of soils, right? So if you have 10 to the minus 8 or 10 to the minus 6, this is like already a factor 100, but you can very likely have that within your modeling domain. Harmonic mean is something that is very often applied, for example, to estimate density if you have different constituents. So you can calculate the density of some kind of mineral matrix or some soil matrix if you have the densities and the mass fractions of the different minerals building up this kind of soil. So that would be an application for how the harmonic mean. Getting a bit more practical here and show you the difference. Let's say you have a couple of soil samples and you get that kind of distribution. So we have 10 to the minus 9 meters per second for 40% of all our samples, 10 to the minus 6 for 30% of our samples, and 10 to the minus 3 for all for the other 30%. So we can do a weighted arithmetic mean based on the volume fractions, and we will get a value of 10 to the minus 4, because of course all are weighted equally. So well, just weighted by the volume fraction. So you will notice those ones are very, very small. So of course those few samples which are close to the 10 to the minus 3, dominate the whole process. If you go for the geometric mean, we will get a value of 10 to the minus 7, which you might consider a much more representative value for that kind of distribution, right? Because it would be close to the 10 to the minus 6. And we have 40%, which are already 10 to the minus 9. So this is somewhere in between here. We can now modify the volume fractions a bit, make it even more extreme, shifting the values to the 10 to the minus 9. And you will see that the arithmetic mean will just change slightly because it's still 10 to the minus 4, which you now might consider even less representative, right? And the geometric mean also, not changing so much, actually, it's from 3.3 to 2.8, but still being to the 10 to the minus 7. So I recommend you take out your calculator, try to reproduce those numbers so that you really understand how to apply these formulas. I just showed a couple slides before, but here I just really want to show you those different kind of representation you get when you apply the different means. And this is not an unusual task. If you're in some office and you have modeling task, you will get the results back from your colleagues doing the field experiments or from the lab. And they will show you, well, this sample with this value, this sample with this value, and now you have to parameterize your model. So this is a realistic task, a realistic calculation that you have to do by yourself to come up with a suitable parameterization. And the question is, what do you do? Do you parameterize your domain with a 10 to the minus 4, or do you represent them with a 10 to the minus 7? What is your modeling choice? You can argue, but you should know that there are different ways to do those kind of calculations. Of course, if we have those kind of samples, we not just measure the mean, but we can also measure the spread. So how much the parameters vary across my samples. And the most usual thing you do is the arithmetic variance, right? You subtract your mean value from each of your sample values, you square the difference, sum everything up, and divide it by the numbers of samples. Right? And if you then take the square root of the variance, you end up with a standard deviation. So this is, basic statistics, first week of semester. When we have those samples, and especially we're also talking about variance and standard deviation, most of you already know, you can make a transition from those discrete numbers of samples towards a continuous probability distribution. Right? So the idea behind it is if you have an infinitely large number of samples, those samples will follow statistical rules, means a discrete, a continuous probability distribution. So I tried to very handy sketch that here. It's not a nice sketch, but the real idea is instead of having those classes, if I have an infinite number of samples, I can make infinite small numbers of classes, and I end up with a continuous distribution. This is handy because probability distributions, which are continuous, can be handled differently from a mathematical point of view. And the most common one which we have is the normal distribution, right? You all hopefully have seen that kind of curves before. It is this classical bell-shaped distribution. It's also called Gaussian distribution or Gauss-normal distribution. And you mainly describe it by the mean, which is here signaled with the Greek letter mu, and the standard deviation signed by the sigma, or the Greek letter. All right, and so if we take the blue line here, it has a mean of 0 and a standard deviation of 0.5. I didn't bother to apply some kind of physical units here. It can't be porosity because we have negative values, but it doesn't matter here right now. It's just about the mathematics. Right, and if I increase my spread, my peak reduces because the integral of my probability distribution will always be 1. Okay, so it goes infinitely here, it goes towards 0, where it's asymptotically approaching 0, put it correctly. So the probability is never 0, but it's asymptotically approaching 0. So the integral over those curves is always 1, right? Because some state has to be matched. So the probability is 1 at the end for all kind of possible states. All right, or if I shift my mean value to 2, then I have the same distribution simply over here because I choose the same spread of 1. Right, so as further my standard deviation is as wider my distribution is resulting. Now you can associate those kind of spread with a probability, so that you, from one single measurement, like let's considering you're doing your simulation, and pardon, you do all your measurements, and you get up with that kind of distribution based on the samples you have. And now you do another sample in the field. There is a 68% probability that this single measurement will be around the mean value plus minus a standard deviation, right, for an additional single measurement. It would be 95% probability that it is around a 2 sigma environment, that's how we call it, 2 sigma surrounding of the mean value. And there would be a 99% probability that it is in a 3 sigma surrounding of the mean value. So you can link those kind of statistical distributions to a probability of occurrence. So the 3 sigma domain is often used as a statistical approach because it's very, very unrealistic. It's just 1% probability that you are further away than 3 sigma of around the mean value, right? That means 1 out of 100 measurements would be out of those 3 sigma surrounding of the mean value. And now you can do something transforming this normal distribution to a log-normal distribution. So again, the hydraulic conductivity here is our application, because it is varying across such a huge range, right? So again, like you would see, the large numbers are dominating our scale, right? If I consider I have a hydraulic conductivity of 0.04 meters per second, but I might have a lot of numbers, so let's say 10 to the minus 9, 10 to the minus 6 meters per second, they all would pile up somewhere here down to 0. So this is what we would call log-normal distribution. So all those kind of values are kind of hidden. So what I can do is I can take the logarithm of those kind of values and come up with a nice probability distribution. But noticing this is the logarithm of those kind of values. Okay, and this is, so we say the hydraulic conductivity usually follows a log-normal distribution. Okay, so this could also be a possibility to more accurately represent your values. And then you all probably know the variogram. Hopefully you know it. If not, you should look it up, which gives you an idea about spatial variability of a random variable. Right, so you're plotting the semi-variance versus the distance of some points, and this is something that's of course now very much related to hydraulic modeling or groundwater modeling, because you want to represent heterogeneity. And now consider those kind of points as you have those kind of measurement points, and you want to know, okay, is this a very local information? Do I have a strong local contrast in parameters? Or is it rather a smooth distribution? Do I have small, small variations across long scales, spatial scales? This might happen, and both cases can be valid. So again, using, for example, hydraulic conductivity as an example, you can have small variations if your soil is very heterogeneous. You might have solid blocks of rock in between here, which have low hydraulic conductivity or almost none. Then you can have on a very small scale very large contrasts, or if you have clay lenses or stuff like this, that could happen. But it can also be that it's a mixture of different kind of soils, or it could also be, well, you have here some sand, but then here you're coming to a more clay-rich material or soil, or even hard rock, which is low hydraulic conductive. You can have those four cases, like strong contrast on a small scale, small contrast on a small scale, large contrast on a large scale, or large contrast on a small scale. So all this could happen, and you can incorporate that one, for example, using interpolation methods such as kriging, into your model, if you have that kind of information. It might be that you do not have enough information or not enough data point to actually do some kind of interpolation. So you can generate random maps of random distribution, for example, of hydraulic conductivity, but incorporating at least that kind of variogram information that you have, knowing like, okay, here I'm expecting really strong contrast on a small scale, so you can generate random maps with that kind of information. Then this is not an exact representation of your field, but it incorporates this crucial characteristic of your field based on your examination, your geological knowledge about the site. Or you can say, well, I don't really know where my sand starts and where my clay-rich material starts, but I know from east to west I somewhere have this transition from sand to clay-rich soil. So you can incorporate that one into your model by having that kind of randomly generated map. Of course, this is this is statistical distribution, but it represents the characteristics of your soil. I would still recommend to vary those kind of maps to see how much your material depends on those kind of random parameters. But often you will see that, for example, you can imagine if you have a small scale heterogeneity here, your flow path will be very tangled, so your macroscopic dispersion is much higher. So if you want to model soil transport, that really won't so much matter if this low conductive point is over here, or if it's over here, or other way around, because the dispersion just simply takes place based on those small scale high contrast in hydraulic conductivity. And this characteristic then is already incorporated in your model, and you can run a couple of models, but of course the exact concentration value would vary, but the overall behavior of the solute transport would look similar. So this is really an important point which you can generate, which you can include into your model, maybe even without the exact parameters. But that's why I say you can do parameter variations to cope that one. If you have enough data points, you can use interpolation techniques such as kriging or other ones to include it. This was already the sum up of me of the geostatistics. So there are a bunch of great books, lectures, exercises about geostatistics in general, and I strongly recommend you to take a look at those. Here I really wanted to focus on geostatistics for groundwater modeling, so showing you how you can link those fields. And this is this is a realistic scenario if you deal with groundwater modeling, right? Can be that your colleagues ask you, or the client asks you, okay, what kind of information do you need from us to come up with a good model? And of course, you said like there are different methods, and you think, okay, I need boreholes, or I need tomographic methods depending on the scale. You need to specify what you need to know, and you want to know how many data points do you need, where do you need your data points, right? This also comes your geological knowledge into play, combining that one, making decisions which are crucial for your model. And then once the data is there, you need to get an idea of how to handle it, how come from data that there is towards a model, right? So there is, I said, different methods. We just, really scratch the surface with the different kind of means in the Lognormal distribution for the hydraulic connectivity. But, those are already crucial methods. Two examples as how you can handle it. Keeping in mind that, porosity is a bit easier because it's all usually within one range. But for the attractivity, because it is spreading among so many decades usually, or can be, that require a bit more attention. And then finally having this important idea about the spatial correlations, right? Do I have small contrasts? Do I have strong contrasts? All those kind of information. And also considering that maybe before you actually, give the orders about what you need on information, running a couple simulations and see, okay, how sensitive is my system with respect to the specific question I want to solve to those kind of informations, right? If porosity doesn't matter, I need to pay less attention to estimating porosity correctly, but maybe doing a bit more effort on estimating hydraulic conductivities, or whatever there is depending on the specific scenario. So I use the scenario of contaminant transport, where I say, well, okay, what is the effect of macroscopic dispersion due to the heterogeneous hydraulic conductivity distribution? And you might want to find out that you want to have, or you need more information around specific regions of your modeling domain, right? Maybe around your pumping station, or maybe around your contamination site. All this, why those kind of first estimated randomly generated maps could help you to come up with a better solution. And yeah, this is already it. Again, my recommendation to you: get familiar with geostatistics, because it can help you a lot when dealing with groundwater modeling, and can be of great help if you want to dig deeper into realistic groundwater modeling. Thank you.